In this question, we're asked to show by counterexample that the statement, if x is an acute angle, then sine of x plus 30 is greater than sine x is false. You can approach this question by trying to put in random values of x and see what happens, but a more rigorous approach will probably be helpful. The way that I would approach this question is that I would sketch a graph of sine x. So here is a graph of sine x. What I know is it crosses here at 180. This is 360. If I mark down here, we have the middle 90 degrees. So I can pick any initial value of x that lies between 0 and 90. It can't actually be 90 degrees, but it can go all the way up to, say, 89 or 89.9. It can go up to, but not include 90 degrees. Now, if you notice, 30 degrees on, actually, if we get right close to 90 degrees, 30 degrees on will be below on that graph. And actually, if we can consider this, there will be a point where on one side of the graph, one side of this point, because of the symmetry, the point here on the left-hand side will be equal to the point here on the right-hand side. Now, if I know the distance between them is 30 degrees, then what I know here for this distance, dividing it into two halves, that's going to be 15, and that half there is also going to be 15. So the angle at this point would be sine 75, and the angle at this point here would be would give us 105. And in fact, if I try sine of 75, we get the answer 0.9659. And if you try sine of 105, then you get the answer also 0.9659. And these are to 4 decimal places. So, therefore, sine of 75 equals sine of 105, and this proves by counterexample that sine of x plus 30 is greater than sine x. And in fact, as long as you pick a value of x that lies between 75, it can be equal to 75 as we've seen in this example, but less than 90, so in that small range there, as long as you pick an initial value of x between there, this will work. Okay, let's have a look at part B. Part B says to find all the values of theta in the range 0 less than or equal to theta less than or equal to 360 degrees, satisfying the equation 15 cosec squared theta plus 2 cot theta equals 23. In this question, you can see we've got a quadratic trigonometric equation. However, we've got mixed terms, so I've got a cosec term, cosec squared term in fact, and a cot term. What I'm going to need to do is I'm going to need to substitute one of these trigonometric functions out of the equation so that I can make this a quadratic all in terms of one trigonometric function. The key to this question is the first order term, the cot theta. Now what this tells me is I don't have a substitution for cot theta, but I do have a Pythagorean identity that involves cosec squared theta. And so that Pythagorean identity is 1 plus cot squared theta equals cosec squared theta. So now I'm going to substitute cosec theta for 1 plus cot squared theta. Make sure you show the full substitution. So 15 times 1 plus cot squared theta. Don't be tempted to expand that first of all. Let's just make this coefficient a little bit clearer. So don't be tempted to expand it in one step. Show the substitution fully first of all, and then start to expand and rearrange. It won't save you much in terms of time or writing. What I'm going to do is I can see that the quadratic term is going to be on the left hand side here, so I'm going to subtract 23 from both sides. So I get 15 plus 15 cot squared theta plus 2 cot theta minus 23 equals 0. and then just tidying up, 15 cot squared theta plus 2 cot theta. We get 15 minus 23 gives me minus 8 is equal to 0. So now at this point I have a quadratic in cot theta. I want to factorize this if I can, if not use the quadratic formula. If I do 15 times minus 8 gives me minus 120. I want factors of 120 or minus 120 that have a difference of 2. And actually if I do plus 12 times minus 10, those factors have a difference of minus 2. So what I can do now is I can split my first order term, the cot theta, into 15 cot squared theta plus 12 cot theta minus 10 cot theta minus 8 equals 0. Factorize the first pair of terms. I can take out a common factor of 3 cot theta. Inside the bracket that leaves me with 5 cot theta plus 4. And then in the second pair of terms, taking out a common factor, I can take out a common factor of minus 2. So I get minus 2 comes outside the bracket. Inside the bracket I get 5 cot theta plus 4, which matches up to my first bracket. So then factorising, taking the 5 cot theta plus 4 as a common factor outside of the brackets. What I get left inside the second bracket, the coefficients of those two brackets, so I get left with 3 cot theta minus 2 equal to 0. So, solving this first bracket, I'm going to add 2 and divide by 3 so that I get cot theta is equal to 2/3. If I take the inverse of both sides so that I get tan theta is equal to 3/2. And so then taking inverse tan, and so finding then theta. So if I take inverse tan of 3/2, we get an answer of 56.3 degrees. And then for the tan function, to generate more solutions, all we have to do is add or subtract 180 degrees to our principal solution. So 56.3 is my principal solution. So if I add 180 degrees onto that, then I get a second solution of 236.3 degrees. And these are to one decimal place, but I'll state the rounding at the end. If I then consider, can I generate any more solutions? If I add another 180 degrees to this solution here, it will fall outside my range. So that first bracket, I've generated all the possible solutions I can. So next, deal with the second bracket. What I'm going to do is I'm going to subtract 4. And I'm going to divide by 5. And so then again, like I did previously, I'm going to take the reciprocal. So what I'm going to get is actually tan theta is equal to this fraction inverted. So I get minus 5/4. Again, take the inverse tan function of both sides. This time what I get is a negative solution. I get actually is minus 51.3 degrees. But we still generate our further solutions in the same way as previously. So with tan, we're just going to add 180 degrees to the solution. So if I add 180 degrees to minus 51.3, I get 128.7 degrees. And then I consider, can I generate any more solutions by adding 180 degrees? And the answer is yes, I can. So if I add to 128.7 plus 180 degrees, then I get a second solution of 308.7 degrees. If I add 180 degrees to this, it's clearly going to go outside the range. So the last thing I want to do is just make sure that it's clear what I'm stating as my solutions. So 56.3 is a solution, 128.7 is a solution, 236.6 is a solution, and finally 308.7 is a solution, and all of these are to one decimal place. Okay then, so let's have a look and see how the marks are awarded in this question. So in part A, there is first of all a standalone mark for choosing a value between 75 degrees and 90 degrees. And then there is a second standalone mark for getting the correct second evaluation that's correct, and a convincing argument. In part B, initially there is a method mark for the correct use of the substitution, which must be shown. There is then a method mark for correctly trying to factorize using an appropriate method the quadratic that's formed from this equation. There is then an answer mark at the stage where both values tan theta equals 3 over 2 and minus 5 over 4. Then there is a standalone mark awarded for getting both solutions of theta from tan theta equals 3 over 2, and then there's a standalone mark for getting for each of 128.7 and 308.7. And notice I've awarded marks at this stage. At this stage, when I've declared my final set of solutions, if I haven't removed any solutions outside that range, you're going to lose 1 mark per solution still included. So it's important, that last line, just to remind yourself that you want to satisfy the inequality at the beginning of the question. Okay, well I hope you understood my solution and that you was able to follow how to mark it.